Okay, so today we're going to talk about the heating curve for water, and we've already talked about parts of this, but now we're going to put it all together, and we're going to put all the pieces together, and all these ideas that we've been throwing around for the last week or so. So over here on this side, we have so we got this graph, and on this side, this is going to be the temperature in degrees Celsius of our substance. In this particular case, it's going to be water. So it's our temperature is over here. Okay, and down here, this is time. Ooh. Time. Okay, so temperature and time. It's in seconds. In order for this to happen correctly, though, the energy that is flowing into our water needs to be pretty constant. That as we add heat energy into our water, this is what happens over time, as opposed to if water just sits there, it's not going to complete the whole graph no matter how long it sits. So we're consistently adding energy into it in order to get this effect in the curve. Does that make sense? Like, okay. So we're going to do a constant energy, constant increase in constant rate. Okay, constant amount of energy per second. All right. Well, we have these three phases, and this slanty phase over here, this first slanty phase, okay, is when our temperature. Well, if this is 0 down here, 0 and 0, so 0 temperature, 0 time. From absolute coldness to some other point, what phase is our water in? It's solid, also known as ice, right? And then over here, okay, well, we also know what we would know what this is here, because this is going to be at what point does our water stop being solid? Yeah, it's 0 degrees Celsius. So actually, yes, there should be a horizontal line here, but it's 0 degrees Celsius. So really, this is negative 273 down here. 0 degrees Celsius, this line here. So what happens at this point? Okay, if we keep increasing heat, what does our ice start to do? It starts to melt. Yeah. All right, so melting, and so this is solid turning into a liquid. But if we're going the other direction, if we're taking heat out of it, then this is also liquid turning into a solid. And what would this process be? It would be freezing. Okay, so if we're going this direction, if we're heating up, then it's solid turning into a liquid. And if we're going the other direction, then it is freezing, liquid turning into a solid. Okay, then once we're done, at this point we are done with our solid, and this whole stuff over here is our liquid. Okay, also known as, we usually call it just water. Right? I just didn't select it. All right. Then we get to this phase over here, and so we keep adding heat, and our water warms up, and then what does it start to do? Okay, it starts to evaporate. Evaporation. And this is the process of our liquid turning into a gas. Okay, or it's known as vaporization. There's a number of terms for it. Evaporation or vaporization. Vaporization. Okay, and if we go the other way, if it's a gas turning into a liquid, what do we call this? This is condensation. Okay, and then up here uh, we have gas. Okay, or water vapor. Okay, now while all this happens, and this is something we struggled a little bit with uh, uh, earlier in the semester, when this is all happening, this ice down here, this ice down here is, well, these changes. What kind of changes are they? Are they physical or chemical? These are physical changes. Okay, we are adding heat into them, but any change of phase is a physical change. Because we will still have, we'll still have our water down here. If it looks like this, so it's a, right, water actually looks like Mickey Mouse. Okay, the structure of it has a central oxygen, and the two hydrogens are kind of off to this. All right. And so when it's a solid, these particles are really close together. They're close together, but they don't have the freedom to move. They're close together, but they have no freedom of movement. Okay, and so what do? We put energy in them. And this process here, this process as we go from solid to liquid, is the process of breaking, wrong break, E-A-K, okay, breaking the molecules apart. I don't want to say apart, breaking the molecules from each other. Because when we get over here to the water, once that's all done, we still have these Mickey Mouses, Mickey Mice, but they are further apart from each other, and they're not larger. They're still the same size. Okay, but they are allowed to move a little bit more. I do need to. Why can't I select you? There you are. They're still close together, but now they are more free to move. Okay, freedom of movement is what we have there. So the molecules are still close together, but they're allowed to move past each other. And this energy right here that took it from a solid to a liquid is the energy that it took to get all of these molecules moving so that they could start moving past each other. Okay. Then we go through the second phase change over here, and at this point our molecules are all over the place. And these guys are, not only do they have freedom of movement, okay, but they are also further apart. Far apart and freedom of movement. And so the energy that goes into that goes into spreading the distance between the molecules and speeding them up so that they aren't attracted to each other. They don't have a mutual attraction to each other. And so they can just, they can be, and that's how our gases expand. That's why if you have water as a liquid, it's in a smaller container. And if you have the same amount of water as a gas, it is many, 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 many times larger in volume. Okay. Now, up until this point, we have discussed these situations, these slanted lines right here. Okay. What would the slope of these lines represent? It would be, right, rise over run, right? So it would be a change in temperature over time, right? Okay, so we have an equation. We've dealt with something that is, as we continue to add heat to a substance, what effect will it have on our temperature, right? Okay, this is our right, so that is our Q equals mc delta T, right? If we're adding heat to a substance, its temperature will increase. All right, so this term right here is for all of these slanty parts. Okay. Now I'll tell you that each one of these has a different specific heat. That there will be a specific heat of ice, and there will be a specific heat of water, and there will be a specific heat of vapor. That each one of these will have a different, and that's why they have different slopes, is because of the specific heat that it takes. For if we're adding energy at the same rate, the increase in temperature will change differently, and that's based on the specific heat. Question? These guys? There's a specific heat, a C for ice, and a C for H2O, and a C for vapor. Okay. But now what we need to talk about are these guys, are the flat things. Why can't we use MC delta T for the flat parts? Yeah, there's no increase in temperature. There's no change in temperature. But we're still adding heat. The heat it's still absorbing heat, and it's still getting into a change in phase. We still have these molecules, instead of being really tight together, okay, they start spreading apart, or not spreading apart, but they're able to move past each other, and that requires some more energy. And then eventually they break free from each other, and they're all flying around with much more energy. How do we measure that amount of energy? Okay, and that leads us to our next equation, okay, in our new, that's too big, Q equals mass times delta H, and in this particular case over here, it's of F for fusion. I wanted that color, and I wanted a smaller brush size. Okay, this F stands for fusion, which is the bringing, making the liquid turn into a solid. Okay, it's the general term for any of this is fusion. This is not to be confused with nuclear fusion. That's a whole other topic we will get to later in the year. Okay, so this is the heat of fusion, or the heat of freezing if you want. Okay, and notice it is just based on the amount of mass that is there. So I'm getting a little convoluted here, but this is for this horizontal part. And then we have the same thing over here, Q equals mass times delta heat of vaporization, VAP. Okay, and it does the same thing. It has the same effect, where this is for this flat part. Okay. Whew, that's a lot. Didn't mean for that. Get out of precision mode. I don't want precision mode. I don't want that. How do I get out of that? I don't want that there. So let's talk this through. If we are going to heat an ice cube, it's somewhere down here. Take an ice cube, I pull it out of the fridge, okay, put it onto a hot plate. It's already lower than zero, right? You guys understand why it's lower than zero? Because if it was at zero, then it would be kind of icy, watery. Okay. And so to turn this ice cube into steam, what are we going to have to do? Yeah, well, we'll add heat. And so the temperature will increase, right? Until we get to our ice water thermal equilibrium thing, but we keep adding heat into it, which is going to do what? Is the temperature is not going to increase for a while. Where does that heat go? It goes into the ice, into the actual disassembly of the ice crystals, right? Turning it into liquid water with the molecules have more freedom to move. Stays at the same temperature the whole time, but it makes that transition. Okay, so to refer back to what we were talking about before with the whole hydro flask and the ice and the water mixture, the hydro flask gets the ice and it restricts energy from entering the system. And so the water that may have been at room temperature and the ice that was well below meet thermal equilibrium somewhere in here, where some of the water is still liquid and some of the water is still ice. And because there's no energy going in, it's stopped. It's halted somewhere in this process. That make sense? Okay. So now we take off the lid and we allow more heat to flow in until what happens right here. Yeah. Well, the temperature can increase because what has happened. But we're constantly adding heat, right? The whole time. So there's that that corner part should be the clue. Yeah, there's no more ice. All of the energy that has gone in, because it's in thermal equilibrium this whole time, okay, when there's extra energy, it goes from the water into the ice, and the water is unaffected because it stays in thermal equilibrium until the change has completely changed, and it's all water, and there's no more need to break the ice particles apart with the energy. So now we can just heat up our water, right? It's like putting it in a tray and we start boiling the water, right? Or we heat up the water until right there, and what starts happening at that point? Yes, it starts to evaporate, and what do we call? Oh, that's right. We didn't put that other term for it down here. In this direction, it's also called boiling, right? when our water gets up to 100 degrees Celsius, it starts to boil. Yeah. Okay. And it takes a while. Have you guys ever made a pot of water and just let it boil down to nothing? Okay. One time I did that in my apartment in college because I forgot I had water boiling. I almost started a fire. Yeah. Let my life live as an example to others. Okay. So we get to here, and all of this heat is doing the same thing that we were doing with the water and the ice, except now it's going from water into gas. And the water will stay at boiling at 100 degrees until it has completely evaporated. Okay, which is one of the coolest things about cooking with water, is that you can put things into the boiling water and you can keep adding heat to it, okay, but it's going to stay at the same temperature. And if you boil something, it won't get hotter than 100 degrees Celsius. Okay, so it's a cool way to like cook frozen foods and that sort of thing, because it's a gentle heat that doesn't get too hot. But anyways, until you get to here when all of your water is evaporated and we're up here in a gas. So each time we go through one of our sections here in our heating curve, we're going to need to use a different one of these equations. Either we'll use MC delta T with our specific heat for ice, or we're going to use, right, so through here, MC delta T specific heat for ice. Then we'll come through here, and this is mass times the heat of fusion, right, as ice is changing. And then over here, we're back to MC delta T because we have changes in temperature. But this time we'd use a C for the water. Then we have our another heat of fusion, or heat of vaporization here. Okay. And then once it all evaporates, then we can start increasing temperature of the gas again. Okay. Okay. This range up here is why pressure cookers are really dangerous. Okay, because if you vent the pressure cooker when it is cooking, the pressure will cause this to extend longer. No, I take it back. It causes this to go higher. Okay, it superheats the water. Okay, and causes it to boil at a higher temperature. Causes it to boil at a higher temperature. So when it does turn into gas, it's at a much higher temperature, and that steam is popping out at like maybe 400 degrees Celsius. right? As opposed to normal 100 degrees Celsius for steam, because it's, yeah, and so it'll really burn you. Steam will like melt your skin or so, out of a pressure cooker. It's really really hot. Okay, so does this make sense to you guys? How we would have to switch between Q equals MC delta T and Q equals MH. Okay, MH and H, delta HF and delta H, these guys have a collective term, and they are called, so delta H of fusion and delta H of vaporization, these guys are collectively called uh, latent heats. It's called latent heat, and it's the heat that is required to go into your substance in order to get it to change from one phase to another. It's called latent heat, L-A-T-E-N-T, heat. Okay, so here we've got an example, and we're going to do, right, so these are examples of these heat kind of problems. So these, by the way, you do not have to memorize these. Okay, I mean, it's kind of a good idea to remember it, but you don't have to memorize them. These are heats of fusion, heats of vaporization, heat capacity of solid water, heat capacity of liquid water. This is the HS and the Cs, right? It's those constants. They will be given to you on any kind of assessment. You do not have to memorize them or write them down. So if we have a cup of water, cools from 75 degrees Celsius down to comfortable room temperature, 20 degrees Celsius, how much energy does it release to the surroundings? Okay, so with our curve, let's bring our curve back. What are we talking about?
Water.
Just water, right? Okay, are we going through any phase change? Nope. So we're only talking about what part of the graph?
The middle part going up.
Yep. We're only talking about the liquid water part of the graph, right? It's going from 75 degrees Celsius down to 20 degrees Celsius, and it's releasing that energy to the surroundings, yeah? Okay, so that's, right, so we're going from about 75 to 20, and that whole range is, in fact, all right, so let me do this. So this whole range is going to go from here. It's going to go from here to about here, and it's just that range right there. All right? Can I select the group? You're not going to let me select the group, are you? That sucks. All right. So that means we're going to use what equation? Q equals MC delta T. All right, so what's our mass? We've got 140 grams. We have C of liquid water right here. So that's going to be the 4.18. 4.18 joules per gram degrees Celsius. And then we have a change in temperature of 75 degrees Celsius minus 20 degrees Celsius. Okay, and you guys can figure that out, and that we've been practicing that for the last couple of days. Okay, but let's take a look at number 2. Suppose during volleyball practice, you lost a kilogram of water due to sweating because we worked you hard that day. Okay, And yes, for those of the uninitiated, yes, you can sweat during volleyball. You just can't sweat during water polo. You can't tell. You're not sweating. You're not sweating. You're not sweating. You don't sweat during water polo. But you're really not because okay. We're going to pause while we settle this argument. So, if we lose 100 grams of water due to sweating, and it all evaporates, how much energy did the water absorb from your body? Okay. So, what I will tell you is when water excretes from your body, what temperature is it at? Ooh, in Celsius. There it is. But you totally Googled it. But that's okay. It's fair. Okay. Yes, body temperature is 37 degrees Celsius, which converts to 98.6. But that's exactly what it does is convert to 98.6. 37 is actually the 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 average body temperature. Um, okay, so we start at 37 degrees, and that water needs to heat up to 100 degrees Celsius, right? Okay, and then you have 1,000 grams of it that goes from 100 degrees Celsius uh, in liquid form to gas. So we really have two phases we're talking about. We're going from about here to here, and then we have to take that 1,000 grams to evaporate. Yeah, so we have two steps we have to go through. You guys with me on that? The water heats up to its vaporization temperature, and then we start losing that heat. Yeah? All right. And I lost. Okay. So our total Q equals MC delta T plus our mass times our heat of vaporization. And we'll pause for a minute. I'll let you guys give that a shot.